Okay, so I'm very happy to be here once again, and we continue our series of complex analysis seminar with Nicola Arcozzi, who's going to talk about a quick proof of Riemann's mapping theorem by following McKean. So now I'm going to disable the microphone of everyone. If somebody wants to enter in the conversation and make a question, just unmute yourself and ask the question. E Nicola, rimetti il microfono perché.
Okay. Do I have the mic?
Nicola, rimetti il microfono, se no non sentiamo.
Okay, okay, I have the microphone. Great. So let me go back to this. Okay, so I'm going to talk about the old business, and there is nothing original. It's just about the paper I read recently and that I liked. So it is about the proof of Riemann's mapping theorem. Riemann mapping theorem says that if you have a simply connected domain in the plane, then there is a conformal map, well, which is not the plane, of course. Then there is a conformal map from the unit disk, or the unit disk or the upper half plane, which is the same, onto this domain. Okay, and so the article I'm going to talk about, it is an article by H.P. McKean, which is one of my favorite, how to say, writers of math, also because his papers are full of ideas, typically concentrated in a few lines, and with no reasonable proof. In fact, if you read that, this paper is from 1999, and the Massanet review says, well, the proof is quick, only in the sense that a careful derivation is replaced by a few short and rather cryptic statements. So the goal of this seminar is just to go through these cryptic statements and to make them, how to say, more orthodox somehow. Just about the Riemann mapping theorem, okay, the proof we teach is using the square root and an extremal problem for the derivative of a map from the domain into the unit disk. It goes back to ideas of Koebe and Bieberbach, so it's very old. But the proof of Riemann was quite different. It was based on the Dirichlet principle, minimization problem for what we call a Sobolev norm, but for the integral of the gradient square of a function. Then probably everybody knows that there was this proof of Riemann based on the Dirichlet principle. Then Weierstrass came with counterexamples to the Dirichlet principle for some differential operators, and then people tried to get new proofs, and it was Osgood, and some people say, some American people say that Osgood was the first great major American mathematician. In 1900, gave a proof of Riemann mapping theorem following the argument of Riemann, but with all details in place. Okay, and there is the book by Courant, the Dirichlet principle, conformal mappings and linear surfaces. It's full of beautiful information, and the first 30 pages are Osgood's proof. Okay, and here is a suggestion of reading. Jeremy Gray, historian of mathematics, I think he's from Australia, wrote a nice article on the history of the Riemann mapping theorem. I think he also wrote a history of complex analysis, which I haven't read, with Bottazzini from Milano. Anyhow, so let's go back to the Riemann mapping theorem. So the Riemann mapping theorem for polygons is a Schwarz-Christoffel formula, and as a theorem, it says that given a polygon, which is a polygon bounded by a simple closed polygonal curve, P, I will use the letter P for both the boundary, the interior, and the closure. So it's okay. So given a polygon P, there is a conformal map from the upper half plane to this polygon. And so the way we teach typically, so there is the orthodox way. It is that first one proves the Riemann mapping theorem using this Koebe-Bieberbach argument. Then we use a Schwarz reflection. I mean, this is what is in Alford's book and many other books. And using Schwarz reflection plus the Riemann mapping theorem, you get the formula of Schwarz-Christoffel somehow. So McKean takes this heterodox view, which is first you prove Schwarz-Christoffel. Then you have, then you make an exhaustion of your simply connected domain by means of polygons, and use some normal families plus the argument principle and other standard techniques, and then you get the Riemann mapping theorem as a byproduct. Okay, so so the punchline is that you can prove Schwarz-Christoffel without the Riemann mapping theorem in a way which is not too hard. So with a few strokes, as he says, although few strokes without many details. And what McKean says in the paper, by the way, is that he gave this proof by himself, and then someone told him that there is a proof like that in a book by Bieberbach. Okay. So let's go to McKean's proof. So what are these maps F of Schwarz-Christoffel type? So we pick W. W here is in the upper half plane. Perhaps upper half plane is this. Perhaps even on the boundary of it. And you consider, okay, here I put, for completeness, I put coefficients A and B. A is equal to 1, B is equal to 0, that's okay. You make an integral of this of a function dw, of the function 1 over minus w to the p naught some power x1 minus w to some other power and so on up to n, where okay, where you have 0, which is x0, then you have x1, etc., up to xn. Okay, and then infinity, let's say that it is x infinity here. And these powers, well, these powers are between -1 and 1, so that the integral converges, right, in the generalized sense. And the sum of these guys have to be bigger than 1. That's important because so you have convergence at infinity on the real line, for W on the real line at least, and also less than 2. Less than 2, it means that there is one of these guys at infinity, p infinity, let's say, which is 2 minus these things. And then we set theta is equal to pi times p. Okay, so theta j pi j. That. Okay. Okay, so this is the map of Schwarz-Christoffel, and this is the map taking the upper half plane to a polygon. Why? Okay, so what is the basic idea? Basic idea is that we have a polygon, like this red one, Q0, Q1, Q2, Q infinity, Q3, Q infinity. And then we have external angles. External angles, which are this one in the picture. So I prolong Q infinity, Q0, and the angle it makes with Q0, Q1 is theta 0. And then I do the same, and then I get an angle theta 1, theta 2, theta 3, and so on. And a nice exercise in say, first high school year Euclidean geometry is that the sum of these guys is 2 pi. Okay. So what we want to show what we want to show is that this map of Schwarz-Christoffel maps into something like this, where these angles theta j are p times pi times tj. That's okay. Okay, angles are not enough because you can do two polygonal curves with the same angles, okay, and one defines the boundary of a simply connected domain, and the other doesn't. Okay, so one has to be careful. Okay, this is some obstruction we have to take into account. I take just a note on the arguments. So if I take, we take our arguments, we take them in minus pi pi, including minus pi. This way, if you have a point x on the boundary and the point w in the upper half plane, the argument of this point is minus alpha, where minus alpha is between minus pi and 0, okay, including minus pi if the point w is on the real axis. And so the argument of those vectors we find in the integral are between 0 and pi, where then you multiply times this p power, and so you get 0 and p times pi, which is 0 theta, where theta is okay, a few things about this map. Well, first it is that F defines a continuous map on the closure of the upper half plane in the Riemann sphere, so including infinity, right? And you can see that because if you make a change of variables, f of 1 over z, and you do calculations, you can also check that the arguments work in all of these. You get in a neighborhood of 0, which is 1 over z is equal to infinity, neighborhood of 0, you get this possibly singular thing over here, but we assume that this is minus Pn is less than 1. Because P0 plus Pn is bigger than 1. Okay. So it is using the open mapping theorem or your favorite tool, maximum principle, whatever. So the boundary of the, if you consider the image of the upper half plane, the boundary is contained in f of the boundary of the upper half plane, where it is possible to have this, because you see, okay, there was this picture with an obstruction. Okay. So what about the arguments? Okay, the arguments of this is the integrand, right? When you consider the arguments, let me make a picture. What happens? Okay, so here it is 0, here it is x1, x2, let's say this. Okay, if you consider x here, okay, if you consider x here, all of these arguments are positive, because you have 0 minus x, x1 minus, all of these arguments are 0, I'm sorry. I have 0 minus x, x1 minus x, and so on and so on. They are all positive, and so the arguments are all 0. Okay, so if x is less than 0, it is 0. But if x is here, okay, then all arguments are positive, but this one, the argument here, which is okay, so the argument of 0 minus x prime is pi. Argument of 0 minus x prime is minus pi, let's say. So the argument of of this is 0 plus 0 plus 0 plus pi times p naught. Okay, and when you pick x here, you have also the contribution coming from this and this and so on and so on, and then you keep adding. You keep adding until in the end, if x is bigger than xn, you have summed all of the arguments, and so you get theta 0 plus theta n, or p0 plus pn times pi, which makes 2 pi minus what I call theta infinity, angle at infinity. Okay, and so when I integrate, I start from q0 is equal to 0. Well, I start from minus infinity, right? Okay, then I have, I start from minus infinity, so I pick the integral from minus infinity to 0 of f of x dx, okay? And, well, let's call it ft dt, let's call it this x, okay? And this is a number which is, I'm sorry, that was a 0. Let me do it better. So let me write it better. When I consider f of x, which is the integral between 0 and x of f of t dt, okay, then f of minus infinity, well, that's, you know, it is some negative number, integral between 0 minus infinity of f of t dt. It is a negative number, which is this one. Okay, we are on the negative, we are minus here. Okay. Then as x goes to 0, the point moves in this direction towards q0, and then I make a jump, as I said before in the argument, this external angle, and then I keep going like this, and then I keep going like this, and then okay, a miracle happens that the last step goes back here. Why? Well, because the map was continuous. We said it before. Okay. So if you, as an exercise, if you drop some of these conditions, so drop conditions. Oops. Wait a second. I touched something on the tablet. Okay. There it is. Okay. Drop conditions. To have a picture like that. I don't know, like that. So if you make some integral to diverge, you get that. But all our integrals converge. So we have this picture over here. Okay, so these sides, L0, L1, blah, 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 and infinity, are determined by these formulas. That's pretty much, right? That's the length of a curve, definition of length of a curve. Okay, so what is the strategy of McKean? The strategy is this one. So fix the angles. So we fix the angles satisfying all of these properties we said before. So the sum of these guys has to be 2 pi. They cannot be too large in absolute value, and so on. Then, given a polygon with n plus 2 sides, well, it must fall in some family of angles, right? because its external angles, they sum to 2 pi, and they are not too large nor too small, so they fall for some n plus 2 tuple of numbers. And then prove that I can choose these points, x1, x2, blah, 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 xn, so that the image of C plus of the upper half plane is exactly this polygon, which is, let's remember, simple and closed. Okay. So that means that after having fixed the angles, I consider a map taking I have a map taking these n tuples of x's to the n tuples of the sides and the map phi is given by these formulas. Okay, that's the map phi, because these sides they only depend on the choice. Given the angles, they only depend on the choice of x1, x2, blah blah blah. Okay. Okay, probably it is obvious for all of you, but I had to think about it for at least 1 minute, and maybe even 2 minutes. It is that you don't need you need just n sides. Okay, like in a triangle, if you know the angles, you only need one side to determine it, and so even in n plus 2 agon, if you know all angles, you just need n sides. There it is. Right. Okay. So we have this map, which is defined by these integrals upstairs, right? The problem is to define the right domain and codomain of the map. Okay. So if you want the proof of McKean to work, by the way, he's quite casual about it. But okay, as a starting set, right? As a domain, you want to have all of the n tuples, 0 less than x1, less blah blah blah, less than xn, with the property that when I consider the Schwarz-Christoffel map, gives a closed simple polygon P with n plus 2 sides. Okay. So it is a set like this. Okay. So it is a set doing what should be. And the image, omega 2, it will be, the L1, L2, Ln, the sided, I don't know why I write sided instead of sides, of a simple closed polygon P, right? So this way, the map phi is surely into, right? Okay. Now, what is kind of obvious until you want to prove it, and but I leave it obvious, it is that these two sets are open. Because if I make a small perturbation to the, about omega 2, that's pretty clear. If I make a small perturbation to the length of one side, keeping the angles, and I had a simple closed polygon, well, I still have a simple closed polygon. It's not that this is going to cross itself, if the perturbation is small enough. And about omega 1, since the integral depends in a continuous way by these parameters x1, xn, so if the image of one n tuple is a simple closed polygon, if I move a little bit one of these guys and make a small perturbation, what I'm doing is just a small perturbation to this L1 blah 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 Ln, so I still have a simple closed polygon. Okay. So they are open. Okay, if you want to prove it, maybe it takes, I don't know, 2 pages or whatever. Then omega 2 is connected. Okay, that's an important point, which is omega 2 is connected. Okay, so that means somehow that given the angles, I can move with continuity from any polygon with those angles to any polygon with those angles. Okay. Okay. So suppose you start with a polygon like this. Okay. I just make it easy for myself. Suppose you start with a polygon like this, and you want to end up with a polygon like this. Well, the angles, right, have to be the same. Okay. Well, just you squeeze this, and you are still in the family of the polygons, and then you have this, and then you start enlarging it until you get to that one, and so you have a curve of rectangles going from your square to the other square, and you can convince yourself that you can do this always, all the time. Okay, so what are the claims? Well, the claims are that this map, taking the boundary points, which are the singularities, the branching points for that integral, to the sides, it is first injective. Second, it is smooth, which is we can take one derivative, actually even more derivatives. Third, that the image of omega 1 is closed in omega 2, which means closed in omega 2, it means that if that means that if okay, if you have that Ln is phi of xn, and this goes to some L in omega 2, okay, that's in omega 2, then there exists x in omega 1, so that phi of x is equal to I. Okay. Okay, that's just elementary topology, but it was never good with elementary topology. It's better to say it. And then third, last thing, it is that phi is open. Okay. After we prove all of these things, well, it follows that phi of omega 1 is equal to omega 2, right? Because phi of omega 1, it is an open set, an open and closed set in omega 1, so it must be union of connected components. I'm sorry, phi of omega 1, it is closed and open in omega 2, so it is the union of connected components of omega 2, but omega 2 is connected, so it is the whole of omega 2. Okay. So let's see that this map phi is 1 to 1. Okay. So suppose there are two maps. Suppose that for two choices of the points x, I have maps, the maps defined at the very beginning, this Schwarz-Christoffel map, maps onto the same polygon. Okay. Then, when I go back and forth, right, I make f2 minus 1 of f1, going from the upper half plane to the upper half plane. This is a automorphism of the upper half plane, fixing infinity, and the automorphism and fixing the origin, because right, because the image of the origin from by f1 and f2 is always the the origin in the complex plane. And there is not much choice. It is an automorphism fixing infinity and the origin. It is C times Z, which means that F1 is of Z is F2 times CZ, and so the derivative follows this rule. And when I compute the derivative, fundamental theorem of calculus, that's the function I was integrating, and okay, I get this, the term on the left is equal to the term on the right, which I can also write in this way. And since these things are the same for all Z, it's very easy to show that, for instance, looking at the behavior at infinity, that C cannot be but 1. And if C is 1, the points are the same, so the map is the same, and so we are done. Okay, so it is 1 to 1. What about smoothness? Smoothness. So smoothness, the problem is that these xj's are in the are points where there is a singularity. Anyhow, so you make a change of variables like this one, which has the effect in the expression giving Lj, which is an integral with here I forgot it was a minus, I guess. You make a change of variables, so you get integral between 0 and 1, and then you see that the xj's appear where they create no problems, and since so you can take derivative since x j is bigger than xj, they are never equal. Okay, so you can take a derivative with respect to xj, and everything works. Okay. Great. So there is the point C. The point C I copied from my notes, also because I didn't have much time. What was the point C? Point C is to show that phi of omega 1 is closed in omega 2. Okay, so what is the basic idea? Basic idea is this one. So let me make some comment and then I write. Okay, suppose I have some xk are, suppose I have x1k blah 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 xnk. Okay, so for a sequence of k's, for k from 1 to infinity, I have these choices of points, and suppose that given this map f, well, which depends on k, of course, I go to polygons with sides L0k, L1k, blah blah blah, L infinity k. Okay, and suppose that as k goes to infinity, that's the point. As k goes to infinity, this Lk, which is this set of edges, goes to some L, but this L is not some degenerate thing, because it has to be in omega 2. So they must be the sides of a bona fide polygon with n+1 sides. Okay. Okay. So suppose that this happens. So passing to subsequences, we can assume that these xjk passing to subsequences, we can assume that as k goes to infinity, they move to some xj's. And okay, the only difficulty is this one. The difficulty is that maybe they clash into each other, right? Maybe x1 is equal to x2. Right. Now, using normal family arguments and so on and so on, and so there is sophisticated stuff. I mean, McKean says that it is a few strokes, but okay. You can show that the map Fk tends to a map F, in which, using compactness, etc., the derivative of F is this one. But using normal family arguments, we also know that the map F is the conformal map onto this picture here. Now, if two of these points clashed together, they just glued together, well, then we know that F, having this derivative with x1 is equal to x2, let's say, cannot map to a polygon with n plus 2 sides, because that analysis we made at the very beginning, right? So they didn't clash. And so they are like this. And so we are done. That's okay. I should make it longer, but basically that's the thing. Oops. Okay. Right. Point D, open. Well, given these properties A and B, so if you have a one-to-one smooth map from an open subset, which you can always assume it is Rn, or open subset of Rn, into Rn, then its image is open. That's a theorem by Brover, I think it's 1912 or something. Okay. There are more sophisticated versions in algebraic topology. Okay, that's invariance of domain, 1912 or so. So well, that's the end. We wanted to show that it is open, right? That the image of phi omega 1 is open. And the conclusion is what I told you, before. Well, I think this is all. Wait, let's.
Okay, so thank you very much, Nicola. Maybe we can unmute and clap. Okay. Are there questions?
May I make a comment?
Yeah, sure.
Sure.
Well, what I wanted to ask is the following, that what the polygons are not such a good argument, is that because they are not invariant, for instance, by transformation of the Riemann sphere, I was thinking whether one can try to copy same proof, but using some polygons, which are polygons in the sense of the Riemann sphere. So with sides which are arcocycles. Okay,
Yes.
use the map of the say Poincaré space, a plane into the disk, and then make this patches of disks. I don't know if there would come out some nicer proof.
Haha. Okay, that's a very interesting question. So when I was reading the first 30 pages of the book of Courant, I just went to look very quickly what was in the remaining 200 and so pages, and there were conformal maps onto domains, as you say.
Mm.
So my advice, that book is beautiful, I think. Also, I find it very hard because it's really a book from the old generation. People who had, how to say, an extremely developed geometric intuition. So the book says, okay, you can see this, you see that, and it takes me hours to understand what they say. And then maybe he spends many pages on something trivial about the Hilbert spaces, which is right. But there is a chapter exactly answering your question in the book. I cannot answer it myself.
No, you see, the one point which struck me is that maybe in this argument, a good point would be to reduce to the case where the domain about which you want to prove the mapping is bounded. This you can always achieve by some, say, Möbius transformation. But the Möbius transformation just destroys a polygon with straight.
You want to have circular. No, you want to have circular arcs. Yes. You can do that. You can do that.
Because in the geometry, in the complex geometry, the right objects are arcs.
Yes. Yeah. Okay. Let me make how to say, a point in favor of polygons. It is that because I know. I know that the invariant thing for the Möbius group is circles and straight lines. So you want to have all of them together. For us analysts, there is also a good point to consider polygons, because when you consider some extremal problems coming from Dirichlet problems, Dirichlet-Neumann problems, and so on, they boil down to things of the make a picture. They boil down to conformal maps onto pictures like this.
Yeah, okay, but it doesn't change if you substitute your straight line by Arco-cycle.
Actually, even more, I would say, basic. For me, even right angles are enough to have a theorem. If you have a theorem with right angles, that's pretty much that's good for most of the things I do for a living. But your question is very good. Yeah, it's
Okay.
Yeah, it is in the classics. Yes.
Okay. Other questions?
May I ask a question?
Yes, Pavel.
Yes, but in this argument, then probably it would be okay to consider polygons with angles pi over 2 or 3 pi over 2.
Yes.
This should make some part of the proof at least easier to follow.
Yes. Yes. Yeah.
Of
course, this is a modern viewpoint, right?
Yes, but
the modern viewpoint is to solve many problems by squares. Yes. I guess McKean is from wanted to have was interested also in triangles. Yes, but you're right. It's after you have if you can deal with plus minus pi over 2 angles, then all of this exhaustion of omega by polygons works perfectly. Yeah.
But then there is another question. There is, of course, this very nice argument to show that the map is injective, which requires that the polygon does not intersect itself.
Yes.
Right. But in principle, I think it should be possible to consider also polygons which like multivariant domains in this case.
I think so. I thought about it, and but I didn't write anything. I thought about in this injectivity thing, what happens if you have two maps going to the same thing? Well, again, the basic idea from the other proof is that you use a square root to open it somehow, or use using a square root is pretty much like having the multivalent function. Or, well, yes.
Yes, there could be some problem, but it's interesting whether there is any way, elementary way to proceed in to make the proof in this case. Then there would be also this proof for multivalent domains. Just a suggestion. Yes.
Yes. No. Yes.
But I do not know how to
It's a
do
good question. My guess is yes. My guess is yes, because the proof does not. Because with respect to the proof of McKean, what you say is just I think it becomes just more a problem of notational complexity that and plus one has, yeah, but I'm sure it can be done. Yes. Well, maybe more than notational complexity. Well, that's a good question. Okay. I leave it as an exercise for myself.
Yes, it can be maybe the proof of that every point has a pre-image can be done by just some continuity and connectivity argument.
Mm-hmm. Yes.
Intermediate value theorem, something like that. Okay, thank you.
Oh, thanks you.
Other questions? So Nicola, I have just a question. Is this idea, I mean, just to use, is it just used to get in the end the proof of a Riemann mapping theorem, or you think this method can be maybe adapted to get information, other kind of information on univalent mappings?
I think no, yeah, okay. There is the second because there is a okay. This paper of McKean is maybe 4 pages. I have it here, and what I talked about was just the first 2 pages. Okay, yeah, the first 2 pages. Okay, what is in the next page before the bibliography? There is a passing from finitely many points x1, xn to infinitely many points, actually even better, to a continuum of points. So instead of having, you have a continuous product, which means that you take an exponential and the logarithm and so on, and an integral in the middle. And then you get some explicit formula for, you get an explicit formula for the conformal map onto a domain with a smooth boundary, in which the curvature of the boundary has a role. Curvature of the boundary is, okay, in the finite case, it's just the angle, but in this case, okay, of course, as in this case, you had to find finitely many points with some properties, just getting to the right side length. In that case, you have a kind of continuous function of side length, which is your unknown, and that satisfies the differential equation. And okay, like in all McKean's papers I've read, well, this is the second time. There is a huge amount of information.
So for instance, I mean, this is
yes,
just...
but it gives information on that.
For instance, can you get something on in this direction on Brennan's conjecture, at least for mapping on this polygon using his idea? Can you estimate, for instance, the derivative and then the integral of derivative or something?
That's very good
because
question.
you have a quite explicit formula.
Yes, that's a very good question. I never thought about it. I haven't thought about it. Yeah, that's a very good question. No, I don't know. By the way, yeah, if you look at this, okay, this is a Massainet. Okay, not only the review was not that great, but like the other paper of McKean I read in my life, it was not a big hit. It was
Okay.
the other paper I read was 10 pages in which there was together Brownian motion, the chaos of Norbert Wiener, infinite dimensional spheres, representations of everything, and so on. Every 10 pages. But it is the basis of 1/2 of my dissertation, of my PhD thesis. So no, your question is good, yeah. But I have, it's too good. I have to think about it.
Okay.
Yes.
Other questions? Okay, so if not, I think we can thank again Nicola for this wonderful talk.
Okay, thanks for